Catch up since last Friday. On the right-hand side of the board is a review of where we left off in Chapter 3. We're discussing fin surfaces, and so far we have two possibilities to find the heat lost by a fin or the fin efficiency. First of all, Table 3.4 is strictly for fins of uniform cross-section. If you recall, there were four different cases, A, B, C, D: convection from the tip, adiabatic tip, prescribed temperature at the tip, and the infinite fin model. Then we also discussed Table 319, Figure 319 and Figure 320. They give you the fin efficiency. Figure 319 for rectangular, triangular fins, Figure 320 for circumferential fins. We didn't discuss it last time, but we also have Table 3.5 as a possibility. Table 3.5 gives you the actual equations rather than a graph. It gives you the equations for different fin geometries. There's, I think, 7 or 8 cases in there. For instance, there's an equation for rectangular fins, triangular fins, pin fins, circumferential fins. So there's various equations given. So if you want the equation for the fin efficiency, Table 3.5. You want to read the graph for fin efficiencies, Figure 319 or 320. Just to go back to a question I had after class last Friday, someone said, well, when would we ever, in case B, an adiabatic fin tip? Why would we want to insulate the tip of a fin? I thought a fin is supposed to, for instance, lose heat. That's true. You don't want to insulate the fin tip. No, that makes no sense. But here's when you would use that. Let's just say this is your automotive radiator model, okay? And here is 2 tubes carrying hot water from your engine to the radiator, okay? We attach a fin between them. You can open your hood and look. There's little tiny thin fins in there connecting the 2 passages. They're both carrying hot water from the engine. Pretty much the base temperature is identical, T base, T base. And you have cool air blowing over this fin, cool air blowing over it. So I'd ask you, for instance, to plot what you think is the temperature across here. So here's T base hot, here's T base hot, here's the middle of the fin there. Draw me a picture of what you think the temperature of the fin is. Well, you know what's going to happen. The fin's hot here. It's going to get cooler as I go this way. The fin's hot here. It's going to get cooler as I go that way. Where these 2 guys meet, no heat's going to cross that center line. No, it can't happen. So what happens is it looks like this. And the key is, at this point right here, dt dx is 0. Well, that's the condition for case B. Look at it in my notes. It says dt dx is 0 for this case. So what you do is you model this fin, you model that half of the fin as if it's a case B with an adiabatic fin tip. So that's kind of like one of the ways that we use the adiabatic fin tip model, okay? It doesn't really occur, but we can model it as being an adiabatic fin tip, like this picture here. The second thing I want to mention, I didn't mention in early Chapter 3, is contact resistance. It's given by the symbol R. T stands for thermal, C stands for contact, RT subscript T, comma C. If I take 2 materials, A and B, and I really look at them under a microscope and look at their surface condition, for instance, take a piece of rough wood and take a piece of, a sheet of aluminum. That's okay. Put them together, rough wood and aluminum. That rough wood is not smooth like the aluminum. There's going to be some air spaces in here. There. These are all trapped air, and you know what happens with trapped air. I told you before, trapped air is a great insulator. So essentially what you've added some thermal resistance when you put material A in contact with material B. So if you want to model that by your resistance model, you have your conduction resistance for material A, a contact resistance from A to B, and conduction resistance for B. Here's R conduction A, here's R conduction B, and here's the thermal resistance T, comma, C. So all you do in these problems, because one of the problems for homework gives you a thermal contact resistance. And the question is, how do I use that? Here's how you use that. Throw that resistance in between those two materials. And he gives you some values in the textbook too of contact resistances, but essentially that's what you're doing. Okay, any questions on those two things then before we go on? All right, so today we're going to work two examples, and we're going to use, this is our resource panel. We're going to use these resources to solve the problem. Our first problem is a rectangular fin. Okay, the rectangular fin has a base temperature of 100. We blow air over it at 20 degrees C. The convection coefficient between the air and the surface of the fin is 100. The width of the fin into the blackboard is 20 centimeters. The thickness of the fin right here is a half a centimeter. We were told the fin is 2024 aluminum alloy. I go to the back of the book under the table for K values, and I find K is 180. You've got a choice of temperatures for K in the back of the book. What temperature should I choose for K? Well, most people will take an average of the base temperature and the fluid temperature. So I'd find K at the average temperature, 100 plus 20 divided by 2 are 60 degrees C. Go to the back of the book, table for 2024 aluminum alloy, under the temperature, 60 degrees C, and find the K value. Okay, well, pretty much we're asked to find the heat lost by that one fin. Find the heat lost by the one fin. Is it a fin of uniform cross-section area? Of course it is, yeah. So we can use table 3.4. So we'll use table 3.4 to start. I'll put that down here. Use table 3.4. Okay, is it a case B, an adiabatic fin tip? No. Is it a case C, a prescribed or given temperature at the fin tip? No. Is there convection at the fin tip? Yes. The problem stated that. The tip is convecting heat away. Is it a case D? I don't know, maybe, maybe not. But I'm going to try case D first. So try case D. When can you use case D? Check MLC. Is it less than or equal to 1/10? If the answer is yes, use case D. If the answer is no, use case A. M equal square root HP over K AC. 100. The perimeter. 2 times a half, 0.005. Let's put it this way. Okay, let's go with the 2 and 2, so T plus W, 20.5 times 2. That's 20.5 centimeters. Yeah, okay. Divided by K, 180. A sub C. Okay, let's do A sub C. Okay, A sub C, cross-sectional area for conduction. T is a half times into the blackboard is 20. So 20.0005. Oh, half a centimeter, 0.005. Got it. To the 1/2 power. Okay, 15.09. So, ml is equal to 0.755. No, cannot use case D. Okay, can't use case D, so now, why don't you just use case A? Well, okay, use case A. Why even check ML? Because case A will always be correct. It'll always be correct. Case D is only correct if ML is less than 0.1. Case A, QF equal, I'll mention capital M in just a second here. Capital M goes in here. Well, the reason why is because if it's case D, if ML would have been less than 1/10, QF for case D is just capital M, 217 watts. But since it's not, I've got to use this big thing here, and I have to go in here and find 4 hyperbolic functions, maybe interpolate. That's a lot of work. So you check this to see if you can get rid of some work, make life easier for yourself. If that's true, the fin can be modeled as if it were infinitely long, and that means QF is equal to capital M. If that's not true, here's the equation. Okay. So now you go to the back of the book and you look under the table, you know, it has x here, and then it has hyperbolic sine here. Then it has hyperbolic cosine here, and tangent there. What is x in that table? X is this thing right here. X is m times L, the argument of the hyperbolic function. M times L is x right there. Okay, put it in there. 143, I think, yeah, 143 watts. Okay, that's what I wanted. I wanted that QF. That's the heat lost by a single fin. All right, now let's take a look. Let's say, well, okay. Let's take a look at other possibilities. Okay, I did this. Okay, go down here. Can I use figure 319 or 320? Not 320, it's for circumferential. But 319, rectangular, my fin, rectangular, good. I'm going to use figure 319. Or use figure 319. Figure 319 looks like this. This is for a rectangular fin. Okay, to do that, to use that graph, I need L sub C and A sub P. In the figure, he tells me L sub C, L plus T over 2. A sub P equal L sub C times T. Okay, let's get L sub C first of all. And then we calculate the profile area. 3 zeros, 26, 25. Okay. Now we get the x variable, L sub C to the 3 halves, h over k AP to the 1 half. And I get 0.553. Okay. Now I go to graph. And from the graph, I find the fin efficiency. It's somewhere around 0.98. It's approximate because you're reading the graph. No, not 98, pardon me. It's 83. 83. It might be 85, it might be 81. It's really hard to read that graph accurately. But that's okay, we're in the ballpark, 0.83. Now, once I get that from the graph, now, I have to find Q. Okay, here it is over here. Once you get eta sub F, you put it in this equation right here. Heat lost by the fin, fin efficiency, times the convection coefficient, times the area of the fin, times TB minus T infinity. Okay, so we got that now, we got that, okay. So put it in there, QF. A to F, H, A fin, T base minus T infinity. Okay, fin efficiency from the graph, 0.83. Convection coefficient, 100. Yeah. Okay, area of the fin touching the air, the front and the back, 0.05 times 2 zeros 5. 0525. And then we have a 1/2 of a centimeter plus top and bottom to top is 05 times 0.2. Temperature of the base 100, air temperature 20. Make sure my numbers are right here. Okay, this guy has to be 0525. Oh, 0525. 2 times, that's front and back, 2 times front and back. Corrected fin length, L sub C times T, L sub C times W, 0525.2, right. You say, well, how about the fin tip? I thought the fin tip lost heat. No, look at the picture again. What are you using now? Are you using L anywhere? No, you're not using L anywhere. What are you using? Oh, L sub C here, L sub C here. You've now corrected the fin tip. With the corrected length, the fin tip assumed to be adiabatic. No heat lost out of the fin tip. So the rules of the game change. Over here, yeah, we used L. Yeah, there's L. You know, we used L over here. When we go and use figure 319, we use L sub C everywhere, as the graph tells us to do. There it is, right there. Okay, which assumes the fin tip is adiabatic. Okay, put this guy, oh, that's it, okay. Same answer, 143, 143. Conclusion makes no difference. Take your choice. You can use either table 3.5 or figure 319. All right. Now we see, yeah, you know, okay, that's good. Let's keep going down our library of possible resources.
Why for QF do you use 2 times the corrected fin length times thickness? Isn't only one side?
Okay, because now the model of our fin looks like this. Here's L sub C. Here's T. And W's out to U. L sub C, T, W. What areas lose heat to air? The top and bottom, okay. There, top and bottom, times L sub C, times, here's the L sub C, times the width, 20. Here's the top, here's the bottom, there's 2 of them. Here's the left-hand side, L sub C, times T, left-hand side, right-hand side, 2, left side, right side.
Can you remind me again, is the P in the other equation up there, is the 2 times 0.25, is that the perimeter?
Oh, yeah, let me see, the perimeter. Yeah, no, it's not the perimeter. The perimeter, the 205, wait, let's see, I'll get the perimeter right here. I don't think that's right. Thanks for getting that for me. Perimeter, okay. Oh, yeah, wait, yeah, okay. Let me do this, it might be helpful. What's that? 20. What's that? 5. What's the perimeter? 5 plus 20 plus 5 plus 20. 20 plus 20 is 40, and a half is 1, 41. 2 times that is what? 41. I'm on.
Gotcha.
Okay. Okay, our resource over here. We've done table 3.4, we've done figure 319. Now, let's try table 3.5. There it is. Rectangular fin, there it is. Find A to F. Use, now I'll say or in big caps again. Use table 3.5. Okay, for rectangular fin, table 3.5. Hyperbolic tangent MLC, A to F. Divided by MLC. We know M and we know L sub C, okay? We just found L sub C right here. We know M, we found M right here. That's there. Put it in there, hyperbolic function, and you end up with the fin efficiency 0.825. Using figure 319, 0.83. Okay, pretty close, you know, less than half of 1% error is right on. And so I read the graph pretty good. I might have read it 83. I might have read it 82. I don't care. Compared to this, I'm off by 1% maybe. Reading the graph is pretty reasonable. But if you want the real answer, there it is with the equation. Now, of course, I put that guy up here with the same area. Why? Because I see LC. When I see LC, I don't include the area of the tip in my equation for QF. So this gives me Q equal 1 for, I think this is a little bit less than that guy. It's like 142, something like that. In other words, there's no change in the answer. It's the same answer. So now you see, if you've got a rectangular fin, you can do it one of three ways. You can use table 3-4, case A, but check case D first. That's the easy way out. Or if you'd rather, you can get the fin efficiency from figure 319 and put it in the QF equation. Or if you'd rather, you can get A to F in table 3.5 and put it in the QF equation here. Your choice. What if somebody then asks you, you know what, I want to know what the temperature of the fin is at the fin tip. Okay, I want to know the temperature of the fin right there at the fin tip. Okay. I can't use figure 319, no. I can't use table 3.5, no. But I can sure use table 3.4. It's right there. There it is. What's x? 0.05. There's an equation there. Put x equal 0.05 in it, crank it out. That gives you the temperature here. How about the temperature in the middle? X equal 0.025. Got it. Put 0.025 in that equation for t as a function of x. And now conclusion, I can find the temperature anywhere along the fin from the base to the tip. Okay. So you can be asked for the temperatures as well as the Q lost by the fin. Okay, so that is the three possible ways to do it. This is long. This is typically shorter, these guys here. Okay. All right, so before I erase this, any questions on this? Okay, so now we're going to put side by side a new example. Okay, this example is a triangular fin. All right, that fin looks something like this. This is the thickness of the fin, T equal 2 centimeters. This is the base of the fin temperature. And the fin base, 2 millimeters, pardon me, I'm going to change 2 millimeters, not centimeters. Okay, the length of the fin from the base out to the tip is 6 millimeters. There's air blowing over the fin at 30 degrees C. And the convection coefficient between the surface of the fin and the air is 40 watts per square meter degree C. So that fin looks like this. There it is, come out of the wall. There it is. How far to come out the wall? I don't know. Wasn't given. W is not given. So what do I want my answer to be? Watts per meter. Q prime. I want Q prime. Watts per meter. Because I don't know how far the fin comes out of the wall. Okay, let's see. The fin is made out of pure aluminum. Go to the back of the book. Under the average temperature. Oh, by the way, T base was 250 degrees C. 250 plus 30 divided by 2. Find K in the appendix. K for pure aluminum at that temperature, 240 watts per meter degree K. Okay, find Q prime. That's going to be watts per meter. Okay. Start again. All right, here's my resources. Table 3-4, fins of uniform cross-section. No, not going to work now. A sub C, where my hand is here, is really small. A sub C is bigger here. A sub C is really big here. Conclusion, A sub C varies with X. Therefore, it's not a fin of uniform cross-section. So ignore that. No can do. Go down here. Figure 319. Oh yeah, there it is. Triangular. I'm going to use 319. There it is. Triangular. Okay. It has the same x-axis parameter, but next to this picture, it says that's LC. Next to the picture, it says L sub C T over 2. Okay. Okay. So I do that. And let's see, my L sub C is 0.006. Did I put? Yeah. Mm-hmm. And let's see, did I get the, yeah, A sub P is 6 times 10 to the minus 6. Okay. Get my x-axis parameter, 0.077. Got it. Go to the graph. As best I can read the graph, I said 0.098. It might be 0.097. It might be 0.99. It might be 0.97. But that's my best guess what it is reading that graph, which is very difficult to read accurately. Okay. Since I used figure 319, I then have to use this. Okay. So I got it here, 0.098. H is 40. Now the area of the fin. 2, there's top and bottom. There it is, top and bottom. No, there's no tip. The tip area is 0. Okay, top and bottom. Here's a right triangle. If I want the hypotenuse, which I do, of course, so here it is, the area. 2 is the top and bottom. Hypotenuse is L squared plus T over 2 squared. Okay, to the 1/2 times W, which is the width, times T base, which now is 250 minus 30. Okay. I don't know W. I want W out of this thing. So I'm going to divide both sides by W. QF divided by W. And I call that QF prime. When I divide this guy by W, of course the W's cancel out. They're gone. So the answer comes out to be 110 watts per meter. You say, well, okay, is there any other way to do this, Sky? And I say, well, yeah, we couldn't use table 3.4. We did use figure 319. I'm going to try table 3.5, because there it is, triangular, table 3.5. So now, put the word or, table 3.5. Okay. Here's what table 3.5 says. The fin efficiency, 1 over ml we have Bessel functions of the first kind. Table B5. Where what's in the parentheses is called x in the table. 2ml equal x in the table. Because the table has the first column titled x, and then it has I1 of x and I0 of x. So you go back there and get that, and you end up with the efficiency 0.960. From the graph, I read 98 from the graph. If I put the numbers in the exact equation, I get 96. Okay, less than 2% error. That's okay. Reading the graph, it's not that bad. It's okay to read the graph, 98. That's close enough, 96. And of course, then if you put that in there, then you get QF prime. I didn't calculate that out. It's going to be less than 110, probably 107.5. It's good. The Q's agree very well. The Q's agree. So your choice for the triangular fin, no on 3.4, yes on 3.19, yes on 3.5. Now take a pin fin attached to a base. There's a pin fin. Slice it near the end, area, pi r squared. In the middle, pi r squared. Near the base, pi r squared. Conclusion, it's a fin of uniform cross-sectional area. I can use table 3.4. Okay, pin fin. Okay for 3.4. Figure 3.19. Nope, there's no pin fins on there. Rectangular fin, triangular fins, parabolic fins. Nope, no pin fin. Do not use figure 3.19 for that. Table 3.5, oh yeah, I put it there for you. Yep, you can use pin fin. You can use table 3.5. That's a pin fin. Now you take the case of a circumferential fin. Table 3.4, uniform cross-section? No, it's not uniform cross-section. The area gets bigger as you go away from the fin base. No. Figure 3.19, no, it's not rectangular, it's not triangular, it's not parabolic. No, not figure 3.19. Table 3.5, yeah, it's in table 3.5. So you can use 3.5. Yeah, or the graph, pardon me. Excuse me, 3.20. You can use 3.20. And I'll put this down here too. Circumferential. So your choice is use table 3.5 or figure 3.20. So what I'm saying is any problem you get for homework or an exam, your first decision is, what can I use and what can't I use over here? Well, we went through 4 kinds of fins: rectangular, triangular, the pin fins, and circumferential. We said yes, no, yes, so on and so forth. So your decision then is which one of those guys do you want to use? Maybe one's easier than another one. You don't want to use these guys? You probably don't. These are not on your handheld calculator, okay? Probably don't. Well, then you're going to do this right here, okay? That's the decisions you have to make then to solve these problems. Okay, so we went through all of that. Yes, sir?
So on a test or something like that, what resources would we have that would influence this?
Table B5, table B1 for the hyperbolic functions. Table 3.4, figure 3.19, figure 3.20, table 3.5. They're all online now on Blackboard under documents, under data package. So you know what to expect when you walk in the door. Yeah. Mm-hmm.
Is the reason why L, C, and L are the same, is it because it comes to a point? Or?
Yeah. L sub C corrects for the real fin to one which would have an adiabatic fin tip. Well, since there's no area there, you can't even speak about adiabatic fin tip. It's the same thing. That's why it comes to a point. Parabolic fin, same thing. Okay. Comes to a point, 0 area is the key.
Okay, thank you.
Okay, now one thing we didn't mention last time I want to finish with today, and this is the last part of this chapter, is we don't normally put one fin on a wall. No, we put hundreds of fins on a wall. So what happens on fin surfaces? Okay, so we have multiple fins on a wall. So we have fins, and then we have bare wall between them. So if you want to find, obviously, the total heat loss by the fin wall, you take Q loss by the fins plus Q loss by the bare wall. Okay. So it's pretty straightforward to do that. What you want to do then, let's put the actual equations down on that for you. So you can define something, let's put this down here as Q total. And I'll define it just a minute. Well, I'll put it down here. N's a number of fins. So this is number of fins on the wall. So if we have 100 fins attached to a wall, N's 100. Times the efficiency of one fin times the area of one fin plus the bare wall, which is A total, minus the number of N times the area, minus area of the fin base, theta B. This is the base area. Okay, I think I've got all that in there. And that's equal to, they make this a little bit simpler. This is the total area. A sub T is the total area. Okay. So I think that's all we need there. Normally, you don't need that longer equation. You just go ahead and use this guy right here. This is the one you'd normally use. Okay. I'm going to make this easier for you. I don't like that. I don't like that. I'm going to just call this area of the bare wall. If there's 100 fins, there's 99 spaces between the fins. So 99 times that distance is the bare wall. Okay. Okay, so if it's circumferential, obviously, we have more than one fin, so here's there's the area of the bare walls losing heat. They lose heat to the air too. The fins lose heat to the air, and the bare walls lose heat to the air. So this is probably the simpler way to do it. Just plug in the numbers there, okay? Okay, so we have finished chapter 3. We'll be starting chapter 4, two-dimensional heat transfer, on Wednesday. So we'll see you on Wednesday.